Hello, everyone, and thank you for watching. In this work, we present Foundry, distilling 3D foundation models for the edge. Our goal is to make large, self-supervised 3D foundation models practical for deployment on resource-constrained devices while preserving their strong general-purpose representations. Recent 3D foundation models achieve impressive performance across many downstream tasks. However, they remain extremely expensive because transformers process large numbers of tokens with quadratic attention complexity. Existing acceleration methods such as patch merger or TOMI reduce the number of processed tokens during inference. But these methods mainly optimize a specific forward pass or a downstream task. They do not aim to preserve the entire representation space of the original foundation model. Similarly, traditional knowledge distillation usually creates efficient specialist models trained for a single task, which limits transferability and generalization. Our objective is different. We want to distill the general-purpose latent space itself into a compact standalone student model. To address this problem, we introduce Foundry, the first framework for what we call foundation model distillation for 3D point clouds. The pipeline follows a simple compress and reconstruct strategy. First, a frozen teacher foundation model processes the input point cloud and produces dense token embeddings. Then our student model compresses these embeddings into a very small set of learnable representations called supertokens using our dynamic supertoken optimization, or DSO module. Instead of preserving every token independently, the model learns a compact basis representing the most important semantic and geometric information. These supertokens are then processed by a lightweight encoder. Finally, our cross-attention upsampling module reconstructs the original dense latent representation from this compressed space. The student is trained using a reconstruction loss between teacher and student embeddings. This forces the student to preserve the structure of the teacher latent space while using dramatically fewer tokens. An important point is that after training, the teacher is no longer required. The distilled student becomes a compact standalone 3D foundation model. We now present the main quantitative results. With only 16 supertokens, Foundry remains very close to the original point JEPA foundation model across multiple downstream tasks, including classification, segmentation, and few-shot learning. Compared to standard compression baselines such as TOMI, PyTOMI, and patch merger, our method consistently preserves better transferability and stronger downstream performance after compression. Additionally, we can use our compress and reconstruct strategy to learn a model with TOMI for being a foundation model for any downstream task. Importantly, Foundry achieves this while drastically reducing the computational complexity of the transformer encoder. We additionally introduce a gating mechanism enabling dynamic budget-aware inference. The gate adaptively decides which tokens should be compressed depending on scene complexity. This allows the model to trade accuracy for efficiency at inference time without retraining. On large simulated scenes, Foundry significantly reduces memory usage and inference cost while maintaining strong performance. This makes large-scale 3D perception more practical for edge devices and real-world deployment. First, these TSNE visualizations illustrate the embedding distributions learned by the different compressed models. Even with only 16 supertokens, Foundry preserves a semantic organization very close to the original point JEPA latent space. The clusters remain well separated and highly structured despite aggressive compression. Here, PCA projections of the learned features in RGB space are shown. We observe that Foundry preserves meaningful geometric structures and object boundaries particularly well. Interestingly, compression often reinforces the most discriminative semantic regions instead of degrading them. Finally, we visualize the selected supertokens and cross-attention assignments. Different supertokens specialize in different geometric regions and semantic structures. This provides intuition for how Foundry compresses dense latent representations into a compact but expressive basis. In summary, Foundry introduces a new paradigm for distilling 3D foundation models into compact and efficient proxies for edge deployment. By learning supertokens as a compressed basis of the latent space, our method preserves strong general-purpose representations while dramatically reducing computation. Thank you for watching.